Welcome! In this video, we'll explore problem number 1974, minimum time to type word using special typewriter. We'll break down the problem step by step, analyze different approaches, and focus on the most efficient solution. Stay tuned as we dive into this interesting problem. Imagine a typewriter with 26 keys arranged in a perfect circle, each key labeled with a lowercase letter from A to Z. Typing a character on this typewriter takes exactly 1 second. However, to move between two keys, you can either rotate in a clockwise or counterclockwise direction, and the time it takes to move is determined by the shortest distance between the two keys. Your goal is to calculate the minimum time required to type a given word on this typewriter. The input will be a single string made up of lowercase English letters, with a length ranging from 1 to 100. The output should be an integer representing the total time needed to type this word, including both movement and typing time. To understand this better, let's look at an example where the input word is ABC. The typewriter always starts at A. First, you type A, which takes 1 second. Then, you move clockwise to B, which is 1 step away, and that takes another second. After that, you type B, which is another second. Next, you move clockwise to C, again only 1 step, adding another second. Finally, you type C, taking 1 more second. Adding up all these times, the total comes to 5 seconds. In another example, the input word is ZA. Starting at A, the first step is to move clockwise to B, which is 1 step and takes 1 second. Typing B adds another second. Next, you move counterclockwise to Z, which is just 2 steps away, taking 2 seconds. Typing Z adds another second. Finally, you move clockwise to A, which is 2 steps and takes 2 seconds, and typing A adds 1 more second. The total time for this word is 7 seconds. Now consider the word ZJPC. Starting at A, the first move is counterclockwise to Z, which is only 1 step away and takes 1 second. Typing Z adds another second. Then, you move clockwise to J, which requires 10 steps and takes 10 seconds. Typing J adds 1 more second. After that, you move clockwise to P, which is 6 steps and takes 6 seconds, and typing P adds 1 second. Finally, you move clockwise to C, which is 15 steps and takes 15 seconds, and typing C adds 1 more second. Adding all these times, the total comes to 34 seconds. When solving this problem, there are a few edge cases to consider. For example, if the input word consists of just one character, the output will always be 1 because no movement is required. Additionally, for letters that are at opposite ends of the circle, such as at NZ, the calculation must ensure the shortest distance is chosen. Lastly, with the upper limit of the word length being 100, it's important that the solution is efficient and handles the input size without unnecessary computational overhead. This problem challenges your ability to work with circular data structures and optimize distance calculations effectively. To begin, let's consider the brute force approach for this problem. The intuition here is to directly simulate the movement of the typewriter for each character in the input word. Starting with the typewriter at the first character, we calculate the time it takes to move from the current character to the next. Since the typewriter is circular, there are 2 possible distances, the clockwise distance and the counterclockwise distance. The clockwise distance is determined by taking the absolute difference between the ASCII values of the current and next characters, while the counterclockwise distance is calculated as 26 minus that absolute difference. For each transition, we take the shorter of these 2 distances, as it represents the fastest movement. On top of this, we add 1 second to account for typing each character. By summing up these values for every character in the word, we get the total time required to type out the word. This approach has a time complexity of O(n), where n is the length of the word, as we are simply iterating through the word character by character. Now, let's focus on the optimized approach and some key observations that simplify the problem. Interestingly, the optimized approach ends up being quite similar to the brute force approach because the problem constraints are relatively straightforward. The first observation is that the maximum distance between any 2 characters on the circular typewriter is 13, which is half of the circle. This is due to the circular nature of the alphabet, which contains only 26 letters. For each transition, the time required is the minimum of the clockwise and counterclockwise distances, plus 1 second to type the character. This insight allows us to simplify the problem further. We just need to iterate through the word and calculate the total time using the same formula as the brute force approach. Given that we already achieve an O(n) time complexity, there's no need for further optimization. The simplicity of the problem ensures that this approach is both efficient and easy to implement. The chosen strategy for this problem involves iterating through the word to calculate the minimum time required for each character transition. This approach is considered optimal for several reasons. First, the problem constraints are small, with only 26 letters in the alphabet and the word length being manageable, so an O(n) solution is more than sufficient. Second, the distance calculation is straightforward and leverages modular arithmetic to handle the circular nature of the typewriter. Third, this approach avoids the need for additional data structures or complex preprocessing, making it clean and efficient to implement. When comparing this strategy to the brute force approach, the latter can sometimes introduce unnecessary complexity, such as explicitly simulating the circular traversal, which might make the implementation less intuitive. By contrast, the optimized approach simplifies the process by directly using the minimum distance calculation. In conclusion, this strategy strikes an effective balance between clarity and efficiency. It directly computes the total time by iterating over the input word and calculating the travel time for each transition, resulting in a clean and optimal O(n) solution. In this problem, we are given a circular typewriter that starts at the letter A and loops back to after Z. The task is to calculate the total time it takes to type a given word. The typewriter allows movement in both clockwise and counterclockwise directions, and the time to move between two characters is determined by the minimum distance between them. To solve this, we first take the input word and initialize two variables, one to keep track of the current position of the pointer, starting at A, and another to accumulate the total time required for typing. These initializations set the stage for processing each character in the word efficiently. Now, we process each character in the word. For each character, we calculate the distance from the current pointer position in both the clockwise and counterclockwise directions. The clockwise distance is determined by the absolute difference between the ASCII values of the current character and the pointer's position. To handle the circular nature of the typewriter, the counterclockwise distance is calculated as the total number of letters, 26, minus the clockwise distance. We then take the smaller of these two distances as the minimal movement required to reach the character. This minimal distance is added to the total time, and the pointer is updated to the current character. Once all characters are processed, the total time represents the solution. This algorithm relies on a few key insights. First, the circular movement of the typewriter makes it necessary to evaluate both clockwise and counterclockwise distances to find the shortest path. By using ASCII values, we can directly compute these distances efficiently without manually mapping the letters. Additionally, the algorithm employs a greedy approach, where at each step, the direction with the minimal movement is chosen to minimize the overall time. The algorithm uses simple variables to track the pointer's position and the total time, and it processes the input string directly without requiring additional data structures. This ensures the solution remains efficient in both time and space. We also need to consider edge cases to ensure the algorithm handles all possible scenarios. For a single character word, the pointer only moves from A to that character, or not at all if it's already A. For example, typing the word Z requires the shorter distance from A to Z. If the input word is empty, no movement is needed, so the total time is 0. Circular movement is particularly important in cases like AZ, where wrapping counterclockwise from A to Z is faster than moving clockwise. Finally, repeated characters, such as in AAA, require no movement between consecutive identical letters, resulting in 0 additional time. Analyzing the algorithm's complexity, the time complexity is O(n), where n is the length of the word. This is because we compute the distances for each character in constant time. The space complexity is O(1), as only a few variables are used regardless of the input size. To illustrate, consider the example word za. The pointer starts at A, and we calculate the time to move to C, then to Z, and finally back to A. Each step involves minimal calculations, keeping the algorithm efficient and straightforward. Let's dive into the detailed walkthrough of this example next. For the input za, we start with the pointer at A and the total time set to 0. First, we process C. The clockwise distance from A to C is 2, and the counterclockwise distance is 24. The minimal distance is 2, so we add it to the total time and update the pointer to C. Next is Z. The clockwise distance from C to Z is 23, and the counterclockwise distance is 3. The minimal distance is 3, bringing the total time to 5, and the pointer moves to Z. Finally, for A, the clockwise distance from Z to A is 25, and the counterclockwise distance is 1. The minimal distance is 1, resulting in a total time of 6. Thus, the total time to type ZA is 6. This Python implementation solves the problem of calculating the minimum time required to type a given word using a circular typewriter. Here's how the code works step by step. 1. Initialization. The function starts with the current underscore pointer set to A, representing the initial position of the typewriter pointer. The total underscore time variable is initialized to 0, which will accumulate the total time required to type the word. 2. Iterating through the word. The function uses a loop to process each character in the input word. For each character, it calculates the time required to move the pointer to that character and type it. 3. Calculating distances. The distance between the current underscore pointer and the target character, char, is calculated in 2 ways. Clockwise underscore distance is the absolute difference between the ASCII values of the 2 characters. Counterclockwise underscore distance is the circular distance, which is the total number of characters, 26 for the English alphabet, minus the clockwise underscore distance. For choosing the minimum distance, the pointer can move in either direction, so the function selects the smaller of the 2 distances using the min function. This ensures the pointer moves the shortest path to the target character. 5. Updating total time. The move underscore time, minimum distance, is added to the total underscore time, along with 1 second for typing the character itself. 6. Updating the pointer position. After typing the character, the current underscore pointer is updated to the current character, preparing it for the next iteration. 7. Returning the result. Once all characters in the word have been processed, the function returns the total underscore time, which represents the minimum time required to type the word. This implementation is efficient with a time complexity of O(n), where n is the length of the word. It handles edge cases like a single character word or repetitive characters seamlessly, as the logic for calculating distances and updating the pointer is consistent for any valid input. This is the Java implementation of the problem minimum time to type word using special typewriter, which mirrors the logic of the provided Python solution. Key differences in Java include explicit type declarations, use of char for accessing characters in a string, and the math library for calculating absolute values. The algorithm calculates the minimum time required to type the given word by considering both clockwise and counterclockwise distances for each character. The total time includes the movement time and 1 additional second for typing each character. To begin solving this problem, we start with the word ABC. First, we initialize the typewriter's pointer at the starting position, which is A, and set the total time to 0 since no typing has been done yet. Next, we proceed to type the first character, which is also A. The clockwise distance to A from the current pointer is 0, as no movement is required. Similarly, the counterclockwise distance is 26, which represents a full rotation around the typewriter. The minimum move time, therefore, is 0. Adding the time to type the character, which is always 1 second, the total time becomes 1. The pointer remains at A after this step, as no movement was needed. Now, we type the next character, B. The clockwise distance from the current pointer at A to B is 1, and the counterclockwise distance is 25. The minimum move time is the smaller of these 2 values, which is 1. Adding the 1 second required to type the character, the total time becomes 3. The pointer is now updated to B. Then, we move to the final character, C. The clockwise distance from B to C is 1, and the counterclockwise distance is 25. Again, the minimum move time is 1. Adding the typing time, the total time becomes 5. The pointer is updated to C, and we have completed typing the word. The final output is a total time of 5 seconds. In the second example, we type the word AZ. We start with the pointer initialized at A and the total time set to 0. Typing the first character, does not require any movement, so the clockwise distance is 0 and the counterclockwise distance is 26. The minimum move time is 0, and adding the typing time of 1 second, the total time becomes 1. The pointer remains at A. Next, we type the second character, Z. The clockwise distance from A to Z is 25, while the counterclockwise distance is 1. The minimum move time is the smaller of these two values, which is 1. Adding the 1 second required to type the character, the total time becomes 3. The pointer is updated to Z, and we have completed typing the word. The final output for this example is a total time of 3 seconds. In the third example, we type the word ZA. Once again, we initialize the pointer at A and set the total time to 0. The first character to type is C. The clockwise distance from A to C is 2, while the counterclockwise distance is 24. The minimum move time is 2. Adding the 1 second required to type the character, the total time becomes 3. The pointer is updated to C. We then type the second character, Z. The clockwise distance from C to Z is 23, and the counterclockwise distance is 3. The minimum move time is 3. Adding the 1 second required to type the character, the total time becomes 7. The pointer is updated to Z. Finally, we type the last character, A. The clockwise distance from Z to A is 25, and the counterclockwise distance is 1. The minimum move time is 1. Adding the 1 second required to type the character, the total time becomes 9. The pointer is updated to A, and we have completed typing the word. The final output for this example is a total time of 9 seconds. The core logic of this solution revolves around the circular layout of the typewriter, which has 26 characters from A to Z. For each character, we calculate both the clockwise and counterclockwise distances using the ASCII values of the characters and pick the smaller of the two as the movement time. Each character also takes 1 second to type, which is added to the move time. The algorithm keeps track of the current pointer, updating it after each character is typed. This ensures that we can efficiently compute the total time required to type any given word using the typewriter. The time complexity of this solution is O(n), where n is the length of the input string, because we process each character in the string exactly once. This is achieved through a single for loop that iterates over each character, resulting in n iterations. Within each iteration, the operations we perform are constant time, or O(1). For example, calculating the clockwise and counterclockwise distances involves basic arithmetic and taking an absolute value, all of which are O(1). Similarly, determining the minimum of these distances and updating the total time and current pointer are also constant time operations. Since these O(1) operations are repeated for n characters, the overall time complexity is O(1) times n, which simplifies to O(n). The time complexity remains O(n) across all cases, whether best, average, or worst, because the algorithm processes every character in the input string exactly once, without any branching or additional iterations that depend on the content of the string. Now, considering space complexity, the solution is O(1), as it uses a constant amount of additional memory regardless of the size of the input. Specifically, variables such as current_pointer and total_time require only a fixed amount of memory. Temporary variables like clockwise_distance, counterclockwise_distance, and move_time are reinitialized with each loop iteration and do not grow with the input size, maintaining constant space usage. Additionally, the algorithm does not rely on any extra data structures such as arrays, lists, or dictionaries that could increase memory usage based on the size of the input. The input string itself is considered part of the given problem and does not contribute to additional space. Therefore, the total space complexity remains O(1), as all memory usage is limited to a fixed, constant amount of space used for variables and temporary calculations. To compare this optimized solution with a brute force approach, consider how a naive implementation might explicitly simulate the typewriter's movement. In such an approach, the algorithm could iterate through all 26 positions on the keyboard for each character in the word, leading to a time complexity of O(n*k), where k is the size of the keyboard. By directly calculating the distances mathematically, the optimized solution avoids this inefficiency and reduces the time complexity to O(n). This is provably optimal because the algorithm performs a constant amount of work for each character, ensuring O(n) time complexity, and its space usage remains O(1) due to the absence of additional data structures. In conclusion, the optimized solution outperforms the brute force approach in terms of time complexity while maintaining the same O(1) space complexity, making it the most efficient choice for this problem. When tackling this type of problem, there are some common mistakes you should watch out for. First, ignoring edge cases is a frequent pitfall. For instance, if you overlook scenarios like empty inputs, single character strings, or special characters, your solution may fail in unexpected ways. It's important to test these edge cases to ensure your logic is robust. Next, using inefficient loops can significantly increase the runtime of your solution. For example, problems involving cumulative sums or prefix arrays often tempt developers to use nested loops, leading to O(n)² complexity. Instead, pre-processing the data with an optimized approach can reduce this to O(n). Another mistake is not validating input assumptions. If you assume that inputs will always fall within a specific range without checking them, you risk runtime errors. In interviews, it's crucial to either validate the inputs or clarify constraints with the interviewer. Lastly, overcomplicating the solution is another issue. While it's tempting to jump to advanced data structures like heaps or tries, many problems can be solved with simpler tools like hash maps. Starting with a straightforward approach can save time and reduce unnecessary complexity. Skipping debugging steps is another common mistake to avoid. If you don't step through your logic with small examples or fail to test intermediate outputs, you may miss critical bugs in your implementation. Verifying your solution with 1 to 2 manual test cases can help you catch these issues early. Now, when it comes to interviews, there are a few key insights to keep in mind. Recognizing common patterns, such as sliding windows, prefix sums, or two-pointer techniques, can give you a significant advantage. These patterns frequently appear in problems, so being familiar with them helps you identify solutions faster. Additionally, clear communication is essential. Walk through your thought process, even when you're stuck. Show that you're thinking about edge cases, complexity trade-offs, and possible optimizations. Finally, optimize iteratively. It's okay to start with a brute force solution. Interviewers appreciate seeing how you refine and improve your approach, as it demonstrates your problem-solving skills. To further enhance your understanding, it's helpful to explore related problems. For instance, LeetCode Problem 1-2 Sum teaches you how to use hash maps for efficient lookups, which is a foundational technique in many problems. Another example is LeetCode Problem 560, Subarray Sum equals k, which involves using prefix sums and hash maps to optimize cumulative calculations. Then there's LeetCode Problem 42, Trapping Rainwater, which showcases the two-pointer technique and highlights spacetime trade-offs. Lastly, LeetCode Problem 1249, Minimum Remove to Make Valid Parentheses, focuses on stack-based approaches to validate strings. These problems not only build your technical skills but also help you recognize patterns and apply them to new scenarios. When solving problems like these, it's also valuable to consider alternative approaches and their trade-offs. Starting with a brute force approach can be helpful. While its complexity is often O(n)², or worse, it's a quick way to validate the problem requirements and test edge cases. However, brute force is inefficient for larger inputs. Optimized approaches, on the other hand, such as using sliding windows, hash maps, or prefix sums, can reduce complexity to O(n) or O(n log n). These methods require a deeper understanding of data structures but offer significant performance improvements. Another consideration is spacetime trade-offs. For example, using additional memory, like prefix arrays, can help reduce time complexity in certain problems. Lastly, the choice between recursive and iterative solutions is important. Recursive solutions can be elegant and easy to implement, but they risk stack overflow with large inputs. Iterative solutions, while sometimes more complex to write, are generally more robust for production scenarios. Weighing these approaches and their trade-offs is key to finding the most effective solution. Great job making it to the end. We've covered the problem, analyzed the brute force approach, and discussed its complexity. Remember, these types of problems build your problem-solving skills. Don't forget to like, share, and subscribe for more insightful coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!